Unit 2. In Unit 2, we're going to take a look at how two variables relate to each other. Remember, one of the big foundational pieces of algebra is modeling the relationship between dependent and independent variables. So in this chapter, we're going to start off by taking a look at direct variation. So two variables are going to be related to each other in a direct manner. As one variable increases, so is the other variable. And this is called a direct variation. So let's start off with a little bit of terminology. First of all, directly proportional is another way of saying direct variation. That is two quantities or two variables that increase or decrease together at a constant rate and can be modeled by the direct variation equation y equals k times x to the nth power. Now take a minute and make sure you copy that formula or that equation down correctly. This is the general form of the direct variation equation, and we're going to use it quite a bit throughout the year. Y equals k times x to the nth power. Now k is going to represent the constant of variation, or the multiple of variation, and n is simply going to represent the power on the independent variable. Now when it comes to finding the constant k, we can do this if we know one relationship or one relation or coordinate x, y of the direct variation equation. All we have to do is substitute that relation in and solve for k, and then we'll end up knowing what the constant of variation is for that relationship. So, for example, let's say you get paid k dollars per hour for babysitting. The amount A you earn babysitting is directly proportional to the number of hours you work. So a direct variation equation that models this scenario would look something like this. A, the amount you make, is equal to k, the dollars you earn per hour, times the number of hours you work. So here's what it means to find k, the constant of variation. Let's say you're going to babysit for 6 hours and you actually receive $54. We want to find the constant of variation. Well, our relation here is 6, 54. That's our ordered pair, or our relation, and we're going to simply substitute that into our equation. We've made $54. I'm not sure how much I got paid. That's my constant of variation in this case, but I did work for 6 hours. Well, in order to solve this for your constant of variation, you're simply going to divide over that 6. And you're going to find that your constant of variation here is 9, and that represents the amount of money you were paid per hour to babysit. All right, in example 2, we're going to take a look at a geometric example, the area of a circle. The equation A equals pi r squared gives the area of a circle. Now, we say that the area A varies directly with the square of r. So now notice the difference. We're squaring that independent variable, the length of our radius. Or we can say A is directly proportional to the square of r. And again here, this is going to give us this formula, A equals our constant of variation times the radius squared. Now, it just so happens we actually already know the constant of variation for the area of a circle. In this case, it's kind of unique. K is actually pi. And that's where we come up with this direct variation equation for the area of a circle. All right, in example 3, we simply want you to get the idea of what it means to be directly proportional as you think about different variables. So here we have the cost of filling your gas tank and the size of your car's tank. So think about how these variables might relate to each other, and you can often think about them on an XY axis. And typically we're going to list our dependent variable first, so the cost versus the size of the tank in the car. Now you could have a very small car like a Mini Cooper, and it might have a small tank of only like 12 gallons, but you might also have a very large car like some sort of SUV, a Land Cruiser, and it might have a tank of 25 gallons. Well, if you think about the cost, these costs would increase as the size of your tank increases. And yes, this would be a directly proportional relationship. So we're going to say yes for this first one here. Now, the next one, we have the height of a bat at baseball and the time after it's hit. So again, if we think about this in terms of a picture on a graph in our first quadrant, we have time on our x-axis, and we have the height of that ball. So as it gets hit, maybe it's a little bit off the ground and rises up into the air, but then gravity starts to take over and it comes back down to the ground. So you can see as one variable is increasing, time, height does increase, but at some point it starts coming back down and decreasing. So here we're going to say, no, this is not a direct variation between these two variables. Our last example for this one here says the amount of rain in a puddle and the number of hours it's been raining. Well, you can kind of picture this. Puddles grow larger and larger, and therefore they have more rain in them as the number of hours it's raining goes on. So yes, this is a direct variation or direct proportionality. All right, when it comes to solving problems involving direct variation, we have a kind of a series of steps that we walk through. So here's what we're going to say. These are your steps that you can exercise when solving direct variation problems to become a mathlete. First step is to really read through the problem and underline the variables that are directly related to each other, and make sure you identify which one is the independent and which one's the dependent. This is going to especially be helpful when you have to graph these. Next up, you are going to write the general form of the variation equation. Now, keep in mind the general form typically just has the variables in it and there are no numbers. Substitute one known relation into the equation to find k, the constant of variation. Then we're going to rewrite our equation using, we're going to rewrite the equation with the value, of k in it, and then we're going to use that equation or use that model to find solutions for other values. So let's get a little bit of practice with that here in our next few examples. Example 4 says the surface area of a cube is directly proportional to the square of the length of the edge. Now I'm going to start with some highlighting here. So this is step number 1. The surface area S of a cube is directly proportional to the square of the length E of the edge of the cube. A cube with an edge length 5 centimeters has a surface area of 150. So here's one of our relations. What is the surface area of the cube of an edge length of 8? All right, so let's start off by identifying our independent and our dependent. Our independent variable here is going to be our edge length. As that edge length changes, as it grows in size, the surface area will also grow. So our edge length is going to be E. Our dependent variable is going to be our surface area. Oops, let's see if I can spell surface correctly. That's our surface area, and we're going to call that S. So our relations look like this, E, comma, S. Now let's substitute in our known relation. Remember we said when E is 5, S was 150. So we're going to start by saying 150 is equal to K times E squared. Now I'm squaring E because remember it's directly proportional to the square of the length of the edge. All right, now this is going to translate into 150 is equal to K times, 5 squared, which is going to be 25. Now I'm going to solve for K. So K times 5 squared, I now need to divide off that 5 squared, which is 25, in order to get K by itself. That means K, my constant of variation, is going to be 150 divided by 25, which is going to give me 6. All right, step number 4 says to rewrite our equation with K in it. So the surface area is equal to 6 times the edge length squared. That is our specific variation equation for this problem. Next up, we're going to find the surface area of a cube with edge length E equals 8. So the surface area should be equal to 6 times 8 squared. Following our order of operations, we need to square 8 first. So this becomes 6 times 64, and that is going to result in, I got to check my math here, 384 4, and that's going to be centimeters squared because we're talking about surface area. All right, one more example for today. Suppose m varies directly as the fifth power of p. So again, going through, I have m varies directly as the fifth power of p. So that tells me my independent variable is going to be m. All right, my dependent variable is going to be p. So to write that general variation equation, I would write m is equal to k times p to the fifth power. Now keep in mind, it is to the fifth power of p. All right, we're told that m is 96 when p is 2. We now need to find our constant of variation. So let's substitute in those values into our equation. 96 is equal to k times 2 to the fifth. And let's solve for k. Well, 2 to the fifth is 32, so that's 32 times k is equal to 96. Next, we got to divide both sides by 32 in order to get k by itself. K is going to be equal to 3. All right, once I found that value of k, remember I'm going to rewrite that formula, and it should look like this. m is equal to 3 times p to the fifth. Finally, my last step in exercising to solve these direct variation equations should be to substitute in the value that I'm trying to find m for a given value of p. Now I want to solve for m when p is 5. So m should be equal to 3 times 5 to the fifth. Again, following the order of operations, I need to do 5 to the fifth first. That's going to give me 3,125. And now when I multiply 3 times that, I should end up with 9,375 for my value for m.